All right, hi Hoover, hi AP Chemistry. This is Unit 7, Lesson 35. This is on formal charge and resonance. So we know that oxygen in its atomic state is a neutral atom with 6 valence electrons. Formal charge is a way of determining the charge on an atom involved in a covalent bond. If the formal charge is different than the normal valence charge of the atom, in this case 6 in the case of oxygen, then the atom and the overall molecule are less stable. Nature prefers the most stable configuration of a molecule. Formal charge of an atom is given by this formula. Formal charge equals the number of valence electrons minus the lone pair electrons minus half of the bonding electrons. And when we get into an example, we'll explain what that formula is really saying. So example, both of the following configurations can be formed using the rules of covalent bonds. So if you followed the rules that we did in the previous lesson to form the covalent bonds for carbon dioxide, you could come up with either of these configurations. They're both valid. You've used all of the valence electrons for 2 oxygens and a carbon, that would be 16, and every element has an octet. So those are both valid configurations. But one of them doesn't appear in nature. One of them does and one of them does not appear in nature. So formal charge is a way of telling which one of these is the more stable one and which one will actually appear in nature. So let's apply these rules up above, and let's just talk about the numbers first and then what they mean. So the formal charge of the oxygen on the left, you do it element by element as you do these. You start out with oxygen. Now oxygen in its natural state has 6 valence electrons. So that first number is the number of valence electrons that the element has just in its natural state when it's not involved in a chemical bond. Oxygen has 6. Then you subtract from that the number of lone pair electrons. So if you count over there, the lone pair electrons are the ones that are not bonding to the carbon. So that there were 4 of those. It's not the number of lone pairs. There's 2 lone pairs, but there's 4 lone pair electrons. So you actually want the number of electrons. So there's 4 of those. And then you subtract half of the bonding electrons. So if you look between oxygen and carbon, you see 4 electrons that are involved in that bond. And you take that half of that number, that would give you a 2. So 6 minus 4 minus 2 gives you 0. So what it means is this oxygen is very stable. Now let's kind of analyze what that formula is telling us. It's saying that 6 is how many valence electrons oxygen likes to have in its natural atomic state. So if you look at what's in the red box there, you can see what you want to see is how many electrons does that oxygen own once it's in that chemical bond? How many belong to that oxygen? Well, the 4 lone pair electrons clearly belong only to the oxygen. They're not attached to anything else. So you count those towards oxygen's electrons. The 4 bonding electrons between the oxygen and the carbon, you can kind of think of it that half of those belong to oxygen and half of those belong to carbon. So that means 2 out of the 4 belong to oxygen. So we have the 4 lone pair electrons plus 2 of the bonding electrons belong to oxygen. That's a total of 6. That means that oxygen is feeling pretty normal. It's feeling pretty natural. It's feeling the way it would as an atom with 6 valence electrons. And so that's what the formal charge of 0 is telling us. That if you take the natural number of valence electrons that an element has and subtract the number that it effectively owns, belongs to it when it's in the chemical bond, then if those two numbers are the same, then it's very stable. In this case, this oxygen is very stable. So oxygen has 6 valence electrons. Oxygen has 4 lone pair electrons. And we take half of the bonding electrons, half of 4, and you subtract that, you just add those together, subtract those, and you get 0. Now let's move to carbon. So carbon naturally has 4 valence electrons. Just get that off your periodic table. It's the 4th element from the left. Okay. It doesn't have, if you look inside that red rectangle, there are no non-bonding or lone pair electrons there, so that's 0. And then there are 8 bonding electrons between the carbon and each of the total of the 2 oxygens together, 4 on each side. So you take half of that, you figure half of those belong to carbon, and then half of them belong to each of those oxygens. Okay, so that's 1/2 of 8. That gives you 4, so 4 minus 0 minus 4 gives you 0. So that carbon is very stable. It's feeling the number of valence electrons that it likes to have in its natural state, which is 4. Carbon has 4 valence electrons, carbon has no lone pair electrons, and we take half of the bonding electron. Okay, so we look at the oxygen on the right, and it's pretty much the same as the one on the left. It's flipped around, but that doesn't make any difference. It has 6 valence electrons. Any oxygen does. It's just whatever it has in its natural state. That first number is whatever it has in its natural state. The next 2 numbers have to do with what it has inside the chemical bond here. So it doesn't have any lone pair electron, it has 4 lone pair electrons inside of that bond, the 2 on the top and the 2 on the bottom. And then it has 4 bonding electrons with the carbon, and you take half of those. Again, add those up and you come out with 0. So if we look at all 3 of those together, all of the formal charges for all 3 elements are 0. That's the most stable possible number that you can have. And so that is a very stable, that is the stable form of carbon dioxide. But what about the other one? Maybe the other one could be stable as well. So let's take a look at its formal charge. So the formal charge of 0 in all elements means that this configuration of CO2 is stable. Okay, now we're going to look at this oxygen. So again, oxygen always starts off, it has 6 valence electrons in its natural state. You can count that there's 6 lone pair electrons, the 2 on the top, the 2 on the left side, and the 2 on the bottom. Those are all lone pair electrons because they're not bonding to anything. So that's a total of 6 lone pair electrons. And then it has 2 bonding electrons in between the oxygen and the carbon, so you give it credit for half of those. So 6 minus 1/2 of 2 equals -1. All of a sudden you've got a charge on that oxygen that's not natural for it. It likes to feel 6 electrons in its valence orbital, but now it's feeling a little bit extra negative charge there. So it's not quite stable. So oxygen has 6 valence electrons, oxygen has 6 lone pair electrons, and we take half of the bonding electrons. The -1 charge on the left oxygen means that it is less stable than a 0 formal charge element. Okay, let's look at the carbon. Okay, so carbon has 4 valence electrons in its natural state. You see that there are no lone pair electrons around that carbon, and there are 8 bonding electrons, so you take half of those and that equals 4. So 4 minus 0 minus 4 is 0. So notice that carbon is stable in either of those 2 molecules, the one with 4 electrons on each side, or the one with a pair on one side and with 2 on one side and 6 on the other. Either way, carbon is stable in either of those situations. Okay, let's take the oxygen on the right. Oxygen has 6 valence electrons. 2 of those in that red box are lone pair, the ones on the far right. And there are 6 bonding electrons between the oxygen on the right and the carbon. Take half of those, and that's 3. So 6 minus 2 minus 3 is +1. So that oxygen on the right is less stable. It doesn't have a 0 charge. It's feeling a slight positive charge other than what it would like to feel in the atomic state. So you can see non-zero charges on the right mean that molecule is less stable. Now, even though those charges add up to 0, -1 plus 0 plus +1, they have to, because it's not an ion. That carbon dioxide is not an ion, it's a neutrally charged molecule. So those have to add up to 0, but that doesn't make it stable. The fact that one side has a negative charge, the other side has a positive charge, would actually make that carbon dioxide a polar covalent bond, not a pure covalent bond. So both oxygen atoms have a charge. This makes the molecule on the right less stable than the molecule on the left. And so this is the configuration of CO2 in nature. Okay, now we're going to get on to a subject we didn't get to in class. It's called resonance structures. It's not a real hard subject. It just has to do with molecules that can form 2 different configurations. Not incorrect configurations like we saw with carbon dioxide, but actually 2 valid different configurations. So a resonance structure is an alternate construction of a molecule. Ozone has the formula O3. Ozone contains 3 oxygen atoms. The central atom is connected to one of the terminal atoms with a single bond and the other with a double bond. So you can see how those two molecules are the same. But since the double bond could be connected on either the right oxygen atom or the left oxygen atom, it can be shown in both configurations with an arrow between them. So that's one way that you would show a resonance structure. You don't know whether that double bond is on the left or on the right. It could equally be on both, and neither one of those is wrong or right. It's just that, well, in a sense, they're both wrong and they're both right. I'm going to talk about that in a second. But that's how you would represent a resonance structure like that. A resonance structure is an alternate construction of a molecule. In nature, however, the second pair of electrons in the double bond is moving throughout the molecule, similar to the electrons in a metallic bond. They're kind of buzzing all around in between those oxygens. So they're said to be delocalized. So ozone can be thought of as having 2 1.5 bonds represented by the solid line and the dashed line. So that's really a more correct representation of what's going on there. That extra pair of electrons that was showing as a double bond is really not just staying over on one side. It's actually buzzing around in between those 2 lower oxygens, or actually in between all 3 of those oxygens, kind of like a metallic bond where they run around in the electron C model, and that's what you have. So that's another representation, and that's actually a more accurate representation of a resonance structure. Now, example, oxygen gas O2 and ozone O3 are both molecules containing only oxygen. Which molecule is more stable? So now we're going to apply formal charge again, but this time it's not to 2 molecules with the same configuration that were derived from the rules of forming covalent bond. These are actually 2 different molecules, and they actually do both appear in nature. But one of them is more stable than the other, so we're going to use formal charge to determine that, just as we did earlier. So, to answer this question, we use the diagram of ozone with 1 single and 1 double bond to compute the formal charge. In other words, if you show 2 1.5 bonds, it's going to show everything as being balanced. So you want to show it the way that we showed it originally, with a double bond on one side and a single bond on the other for the ozone, for the O3. So let's first analyze the O2 molecule. So oxygen has 6 valence electrons. The one on the left has 4 lone pair electrons, the 2 on the top and the 2 on the bottom. And then it has 4 bonding electrons with the other oxygen, so you give it credit for half of those. And 6 minus 4 minus half of 4 is going to give you 0. So the oxygen on the left of the left diagram, the O2, is very stable. The oxygen on the right is exactly the same, it's just flipped around, so it's also 0 and it's also very stable. Now let's look at ozone. Let's look at the oxygen on the left, because the oxygen on the left and on the right are not the same now, or the one in the center. So the oxygen on the left is 6 valence electrons in oxygen minus 4 lone pairs, those 2 on the lower, those 4 electrons in the lower left of that diagram, minus half of the 4 bonding electrons. So 6 minus 4 minus 1/2 is 0. So that oxygen on the lower left side of the ozone is actually stable. Now the one in the center, it's 6. That has 2 lone pair electrons, those 2 at the very top, and it has 6 bonding electrons, 2 with the oxygen on the right and 4 with the oxygen on the left. That's a total of 6. So half of that is +1. So the oxygen in the center is actually less stable. It has a +1 charge. And finally, the oxygen on the right has 6 valence electrons minus 6 lone pair down there on the bottom right, and half of 2 bonding electrons, and so that gives it a -1. So therefore, O2 is more stable than ozone. Now ozone does exist. It exists up in the upper atmosphere, and it's one of the things that filters the sun's rays protects us from the sun's rays. However, it is not as stable and does not appear in nature down here closer to Earth, but just in the upper atmosphere. So O2 is more stable than O3, which is why it is more common on Earth. Okay, that was it. That was a shorty. So that takes care of that of formal charge and resonance. And that's pretty much all there is to know about it. It's not a complex subject. A little practice, do the assignment, and you should have that down. Okay, try to get these done by Wednesday. We're going to move into a totally new subject on Wednesday. We're going to move very quickly between now and winter Christmas break, so try to really carve out the time for this class, and I'll have things up and ready for you in a timely manner, and you can get them done on schedule. Okay, so we'll see you in class next time.